Welcome to the video for Lecture 24, Section 2. This video shows some examples illustrating how to model impulse inputs and sinusoidal inputs using MATLAB. All the previous MATLAB examples we have used step changes. MATLAB can handle impulse and sinusoidal inputs too. For this first example, let's assume that we are interested in seeing how the liquid level in a tank changes in response to an impulse addition of liquid. For this problem, we have a single tank. We have an uncontrolled input Q0 and an adjustable input Qn. We have a liquid level transducer that measures tank fluid depth and uses that to adjust the flow of Qn. Now let's assume that at t equals 0 we add a bucket of liquid to the tank, and we ask the question, how does the fluid depth vary with respect to time? Here is the block diagram for the single fluid tank. With this block diagram, you can see that we have decided to use proportional plus integral control. The actuator is being modeled as a simple gain given by kV. The liquid level transducer is being modeled by a first order response with a gain of 1 and a time constant of tau LLT. And the process is described by the liquid level transfer function for a single tank from Section 9 in the course packet. Here is the regulator problem transfer function. After some simplification, we can write the regulator problem as shown at the bottom of the slide. Now if we assume that we have a unit impulse addition to the tank, that means that the transfer function Q of S equals 1. Here are the time constants and the fluid resistance value. This slide shows the time-dependent tank fluid depth response to a unit impulse input when the controller is using proportional plus integral control. As expected, we start with a higher fluid depth, but then we go negative. What does a negative fluid depth mean? This is a good time to remember that this graph is based on deviation variables, which means that the steady-state fluid depth was 0. The negative fluid depth in this graph means that the fluid depth is less than the steady-state fluid depth Z sub S. If we add the initial steady-state fluid depth to the results, we hopefully will not have a negative fluid depth. This makes a good example to remind you to watch and think about the results obtained by the model. Think carefully when you get some results. For the next example, let's use the dye mixing problem we've used before. And we will use proportional plus integral control, and we will use either an impulse or a sinusoidal input function. For us to use sinusoidal input, we will need to use a new MATLAB command, LSIM. Here is the dye mixing block diagram we found before in Section 20. Here is the regulator problem, transfer function, and a few MATLAB commands. The first MATLAB command defines the transfer function for proportional plus integral control. The second MATLAB command is the transfer function describing the dye concentration in the tank. The third MATLAB command defines the transfer function for the Km transform, the actuator, and the conversion term Cm over Q. The last MATLAB command fills the Y3 array with the time-dependent response to a unit impulse for the regulator problem. The word impulse is used to tell MATLAB to use a unit impulse input change. The transfer function equation is G2 over 1 plus KPI times G2 times G3. The time array is defined by T but is not shown. This slide shows the plot of Y3, which is the time-dependent dye mixing problem concentration in response to a unit impulse. Again, the graph produces negative dye concentrations because the graph shows the results using the deviation variables. To get the true results, we need to add back the original steady-state dye concentration. The course packet also shows the regulator problem response. For the last example, let's use the dye problem but use a sinusoidal input function. When we use sinusoidal inputs, we need to use the LSIM command and the linear time invariant transfer function. We define the sinusoidal function U by the amplitude A times sine and the sine wave frequency theta and the time function t. This slide shows the MATLAB commands to define the sinusoidal function U and the regulator problem where the inlet dye concentration is changing with a sine wave. The last command fills the array Y2 with the time-dependent response of the transfer function G1 using the sine wave function defined by U and the time array t. This slide shows the time-dependent sinusoidal input and the regulator problem response. The blue line is the input, which has an amplitude from +1 to -1. The green line is the response. Some things we can see from the response are that the control system reduces or attenuates the change in the process output. One thing that we can see from the response is that the control system reduces or attenuates the change in the process output. The mixing tank output response varies from about +0.1 to -0.1. The output fluctuation also lags the inlet fluctuations, which means that the output has a lag phase shift. This brings me to the end of the Lecture 24 Section 2 video. Write down any questions you have and bring them up in class.